Welcome students, I am Sudipto Karmakar, Assistant Professor of Physics, SVIST, and in today's class we are going to derive Wien's law of radiation from Planck's law of radiation. Now, the energy density of blackbody radiation for wavelength range lambda to lambda plus d lambda according to Planck's law of radiation, it is given by E lambda d lambda equals to 8 pi hc by lambda to the power 5 into 1 by e to the power hc by lambda to the minus 1 d lambda. This is the expression for energy density for wavelength range lambda to lambda plus d lambda according to Planck's law of radiation. Now, we are going to derive Wien's law of radiation from this from Planck's radiation formula. We all know that Wien's radiation formula is only applicable for shorter wavelength range. So, in short wavelength range, that is lambda, it is very low or very small, and we are also taking lower temperature limit. Also, if temperature of blackbody capital T is also low. So we are taking two particular assumptions or approximation. The first one is we are taking the wavelength of the radiation, it is very small, or we are taking it in short wavelength region, and also the temperature of the blackbody is also low. So in that limit, in this limit, the quantity hc by lambda kt it becomes very large, that is, it is much greater than 1, because we all know that if the denominator of any ratio becomes very small, then the total ratio becomes very large. So thereby, as you can see, lambda and t, these two quantities are in the denominator of the ratio. So that is why the total ratio becomes very large. So it is a large quantity. So for that reason, this term e to the power hc by lambda kt, it also becomes very large. So therefore, e to the power hc by lambda kt, it is also much greater than 1. So in that limit, since this quantity, this particular quantity becomes very large, so we can write e to the power hc by lambda kt minus 1, it is almost nearly equals to e to the power hc by lambda kt, because this particular term is very large. So thereby we can drop this minus 1 term. That means if we subtract 1 from this large quantity, so the net result will remain almost invariant. So that is why I am dropping minus 1 term. So this is my equation number 1, and this is our relation or equation number 2. So if I put this particular approximation in relation 2 into relation 1 or equation 1, so we get therefore from equation 1, what do we get? From equation 1, we have on the left hand side, as you can see, in the left hand side we have E lambda d lambda, so I am writing it again, E lambda d lambda, it is equals to 8 pi hc, this is a constant term, 8 pi hc divided by lambda to the power 5 into, we are going to approximate this quantity, that is e to the power hc by lambda kt minus 1. It is nearly equals to e to the power hc by lambda kt because this term is very large. So we can drop this minus 1 term. So it becomes 1 by e to the power hc by lambda kt into d lambda. Okay. Now, after simplification, we have on the left hand side we have e to the power e lambda d lambda. It is equals to 8 pi hc by lambda to the power 5 into e to the power minus of hc by k. H is Planck's constant, c is velocity of light, k is Boltzmann constant. So therefore, this total quantity becomes a constant. Okay, by lambda kt, because lambda is a variable for this case and t is also a variable. So therefore, we are taking hc by k divided by lambda t into d lambda. Now, what do we have here? In the first term, we have 8 pi hc, which is nothing but a constant. 8 is a number, pi is obviously it is also constant, h is Planck's constant, c is velocity of light. So therefore this total term becomes a constant. So therefore we are writing again e lambda d lambda equals to this term. I am writing here 8 pi hc, that is equals to a. Here a is a constant, right? Here a is a constant and hc by k, it is also a constant. hc by k, I am writing it as b, which is another constant. So if I put the substitution that 8 pi hc equals to a and hc by k equals to b, if I put this a and b values in this particular relation, then we have a by lambda to the power 5 e to the power minus of b divided by lambda t d lambda. So this is our well-known Wien's law of radiation. This is our well-known Wien's law of radiation. So we have derived Wien's law of radiation from Planck's law of radiation in shorter wavelength range or in shorter wavelength limit. I hope it will help you in your semester exam. Till then, thank you for watching.